Hi, my name is Nasharina. My matrix number is 200641. So you guys are looking for design of a gas power cycle for internal combustion engine that is suitable to produce net work output in a range of 500 to 600 kilojoule per kilogram, with including the PV and TS diagram. So we came with a solution by choosing the Otto cycle, ideal Otto cycle that has compression ratio of 8. With at the beginning of the compression process, the air is at 85 kilopascal and 320 Kelvin. The temperature at the end of the isentropic expansion process is 2000 Kelvin. By using specific heat values at room temperature, and also by utilizing the cool air standard assumption, we can calculate and determine the temperature and pressure for every point, and the amount of heat transfer in kilojoule, the thermal efficiency, the network output, and also the backward ratio. So I want to explain a little bit about Otto cycle. So Otto cycle is the ideal cycle for spark ignition reciprocating engine. The Otto cycle is a set of process by spark ignition internal combustion engine, whether it is 2 strokes or 4 strokes cycle. These cycles will complete 2 revolutions for each thermodynamic cycle. Specifically, the maximum and the minimum cylinder volume ratio when the piston is at the top of or at the bottom of the strokes. Maximum cylinder volume is when the piston is all the way down or at the bottom dead center, or we call it as BDC, while the minimum cylinder volume is when the piston at the top dead center, or TDC. Due to high pressure gases, it forces the piston to go down, which is it turns the force to the crankshaft. It make the crankshaft to rotate, and it will cause to produce the work output during the expansion strokes. And towards the end of the expansion stroke, the exhaust valve open, and the combustion gas that are above the atmosphere pressure will rush out in the cylinder through the open exhaust valve. The process is called exhaust blowdown, and most combustion gas leave the cylinder by the time piston reach the BDC. Now the piston moves upward one more time, and it purges the exhaust gases through the exhaust valve and down a second time, drawing in fresh air mixture fuel through the intake valve. So this is how 4-stroke cycles looks like. The example of application of Otto cycle describes how internal combustion engines that use gasoline work is like automobiles and lawn mowers.
My name is Kasturiamani bin Rizam, and my matrix number is 200624. As for my part, I will explaining about the internal combustion engine of Otto cycle that we have chose. So firstly, I'll be explaining about the parts of the internal combustion engine. As for the first part is the intake valve. The intake valve is where the valve, when it's open, the air will enters into the engine through it, while the outake valve is where it lets go the heat after the combustion occurs, and the piston head where it controls the expansion and also the compression pressure when it comes up and down during the engine's undergo, while the spark plug is where it releases some gases that causes the combustion to occur in the engine. As for the first phase, the intake valve will be open and the piston heads will go down. Therefore, it will let in some air enter into the enter into the engine. Therefore, the intake stroke will be occur in the PV diagram, and that is where the first temperature is taken into the TS diagram. As for the second phase, the intake valve will be closed and the piston head will be go up. Therefore, it will cause the air some compression and makes the pressure to increase. Therefore, pressure 1 to 2 will be increased in the PV diagram. And also, the temperature 1 increased to temperature 2 in the TS diagram due to the pressure. As for the third phase, due to the high pressure of compression in the engine, the spark plug will release some gases and it will cause some flame, or we call it as combustion in it. Due to that, heat addition will occur and temperature in the S diagram from temperature 2 will be increased to temperature 3, and also the pressure will increase due to the heat addition from pressure 2 to pressure 3 with the same volume. As for the fourth phase, the piston head will go down and causes some loss of pressure. Due to that, in PV diagram, pressure 3 will drop to pressure 4 and causes some isentropic expansion due to the same isentropic of S3 and also S4. And because of that, the temperature will also decrease as pressure is directly proportional to the temperature. As for the final phase, the outlet valve will release some smoke due to the combustion and the heat piston will stay down. And because of that, heat rejection occurs in the PV diagram, causes the pressure to decrease back to 1. So, and also the TS diagram, the temperature will decrease back to the first temperature that occurs. So that is all for the Otto cycle that consists in the combustion internal engine that we chose.
My name is Muhammad Hidayat bin Zari. My matrix number 20725, and I'm going to present to you the calculation of our design. Okay, first we need to understand the PV and TV diagram of the Otto cycle, where we need to understand from the every point, from the work in, work out, and Q in and Q out of the cycle. And this calculation is divided to two parts, where called as standard assumption and as standard assumption. Let's go to the called as standard assumption first. The assumption are temperature 1 is 320 Kelvin, pressure 1 85 kilopascal, compression ratio equal to 8, and maximum temperature T3 is 2000 Kelvin, and last but not least K equal to 1.4, where is practically important in the called as standard assumption. For the process 1 to 2 is the isentropic compression, where we can use the formula R power of K minus 1 and R equal to K to get the temperature 2 and pressure 2, where it is 735.17 Kelvin and 1562.23 kilopascal. Next is process 2 to 3, where constant heat addition occur. T3 is a T max, right, for the 2000 Kelvin, and the pressure 3 we can get by using the linear equation between point 2 and point 3, where 4249.99 kilopascal. Last but not least, process 3 to 4, where the isentropic expansion, and it basically we can use also the formula of R power of K minus 1 and R equal to 1 K, where we get T4 is 870.55 Kelvin and pressure 4 231.24 kilopascal. So let's go back to the equation where we need to find W work net, back work ratio, and the Otto efficiency. Okay, for the work net is we need to calculate between Q in minus Q out, where we got 512.86 kilojoule per kilogram. So we are in the range of 500 to the 600 kilojoule per kilogram. For the back work ratio is the work compressed over work expand, where we get 0.367C or 36.76%. While the Otto cycle efficiency is the work net over Q in. We got 56.47%. It quite high for the efficiency for the Otto cycle. Okay, next is the standard assumption. The assumption is just similar for the cold air, but the main different thing is K is not equal to 1.4. This is because it quite difficult for us to calculate, where we need to use the steam table and the interpolation between point A and point B. For example okay, let's go. I will show you some. For the first process is 1 to 2 is the isentropic compression. Okay, T1 is 320 Kelvin, right? So we need to detect the internal energy and the VR1, where we need to use the ratio to get the VR2, which is 66.08. Next, we need to calculate the temperature 2 and the internal energy 2 by using interpolation from the steam table. And that we can get the 713.89 Kelvin and 523.31 kilojoule per kilogram. For the pressure, we can get the pressure 2 is 1517.68 kilopascal. For the pressure 2 to 3 is a constant heat addition, so it quite easier for us where we get to detect from the steam table only for the third temperature, which is 2000 Kelvin. So the pressure is we got 4251.85 kilopascal. For the process 3 to 4 is the isentropic expansion, which we need to use similar calculation from the pressure process 1 to 2. So we got the temperature 4 is 1050.05 Kelvin and the pressure 4 is 279.04 kilopascal. And go back to our main question, which we need to calculate work net, back work ratio and the Otto cycle. Where work net we got 581.78 kilojoule per kilogram. Back work ratio is 41.40% and Otto cycle we got 50.35%. It is different between the cold air standard assumption and the air standard assumption because different one thing variable and we got different result. And that's all from me. Proceed to the next.
You might be wondering why the cold air standard assumption and also the air standard assumption values in terms of work net, backward ratio and also the efficiency is different. So let me tell you why. This is because the cold air standard assumption consists consistent specific heats, which is the K. In the calculation before, we assume the K is equals to 1.4, which means the K overall for the specific heats through the phases is constant. While as for the air standard assumption, it consists variable specific heats, which means the K is not constant and is not the same as 1.4 as we assume for the phases is constant. While as for the air standard assumption, it consists variable specific heats, which means the K is not constant and is not the same as 1.4 as we assume for every phases. Due to that, the variable might be changed for each phases. Based on the outcome result, we can see that the cold air standard assumption has higher efficiency than the air standard assumption. We can conclude that the cold air standard assumption consists better performance than air standard assumption. It is because the variable of the specific heats K, the K in the constant specific heats, which in the cold air standard assumption can relate with the performance. It might be because the air standard assumption performance might be not consistent and can be increased and also decreased in times. Therefore, the efficiency of the cold air standard assumption way much better than the air standard assumption. Furthermore, we can see that based on the result in the calculation, the cold air standard assumption has lower value of the net work than the air standard assumption. This is because we can see that the cold air which enters into the engine consists lower usage of the energy than the air standard assumption. It shows that we can save much more energy cost of electricity than the air standard assumption. And finally, as for the back work ratio in the cold air standard assumption, much more lower than the back work ratio of the air standard assumption. Needless to say, due to the lower usage of the energy, it can increase the performance of the engine. Due to that, the cold air standard enters the engine way much better than the air standard assumption. That is all from me. Thank you.
Alright, we proceed to the conclusion. In conclusion, the efficiency of Otto cycle will increase with the compression ratio. However, the compression ratio of Otto cycle is limited because we need to prevent the uncontrolled combustion, which is known as knocking. Although for a given compression ratio, the Otto cycle has a higher efficiency than diesel cycle because the diesel engine can be operated to higher compression ratio. Otto cycle efficiency is higher than diesel cycle efficiency for the same compression ratio and heat input because in Otto cycle, heat rejection is lower. But when Otto cycle is compared to the Carnot cycle, the efficiency of Otto cycle is lower than Carnot cycle. This is because of Otto is more complicated than Carnot cycle. Besides, the cylinders are not perfectly insulated from engine block, so heat energy is lost from each cylinder by conduction. Moreover, the working gas of Otto cycle, which is gasoline, is polyatomic molecules such as octane. So it is not monoatomic. However, Otto cycle is more compact and occupy less space, which gives convenient experience to user. Otto cycle did not require any equipment such as boilers, feed pump and condenser, which can lead to higher output per unit weight, and also it will cost more. Otto cycle has higher brake thermal efficiency as only a small fraction of heat energy of the fuel is dissipated through the cooling system.